choose of the many papers that he has authored, written, to choose two which he thinks are he's proud of or his most favorite papers. And he sent me, of course, 4, but then I chose 2 from the 4. And these are the ones that are shown in my screen. I hope everyone is seeing my screen now. So I'm going to read the titles of these papers. The first one is Photonic Crystals from Ordered Mesoporous Thin Film Functional Building Blocks. And the other one is Porous Supramolecularly Templated Optical Resonators Built in 1D Photonic Crystals. I'm a biologist by training and can hardly understand what these papers are about, but then apparently many people in the world were very interested in these papers because they are highly cited, high impact papers. One of them was published in 2006 and the other one in 2011. Papers are the written evidence, are the documents of many activities that go beyond scenes. And in my next slide, and then, sorry, as you can see the papers, here you see the name Hernan Miguez is here and Galo is the last author, but then you see other people, like 5, 6 people here. And then in this other paper, you see again, Hernan is the last author here and Galo is here as well. And there are other people. So as I said, this is the written evidence, but there is a lot of activity, lots of things that go behind the scenes. And in my next slide, Galo, in my next slide, yes. We have Galo and Hernan here in UNSAM. This is Galo's office at the campus, our campus in Buenos Aires. And I like this picture because they are working, they are thinking, they are brainstorming. And this is something that, that most people don't know, that science is about teamwork. These days, it's not usual that you have a scientist that can work on its own. So you have people thinking together, and that is really what happens behind the scenes. There are times not everything is happiness, and there is lots of frustration and other things that happen as well. And in my next slide, please, Galo. We have Galo and Hernan here, and this was a seminar that we had in August 15th, August 2018, when Hernan came to UNSAM for 3 months to visit Galo's laboratory, and he gave a seminar again. This is something that is the front end of what science is. And then today, both of them are going to talk about what they do, what they love, and they're going to answer some of the questions that we have from the audience. And without any further ado, so one more thing, people that want to ask questions, please do so in the chat box below, and then we are going to deliver them after both talks. We are going to deliver them to the speakers. And Galo, I'll hand it over to you now.
Good. Thank you very much. Susana, thanks Hernan for coming. We are, the dynamics of this is giving 2 short presentations, and mine, I will make it so as fast as I can. I will talk about several aspects from a chemist's point of view of some applications of nanotechnology in the front line of research and applications, in particular in energy, environment, and health. The idea and the dynamic idea was very nice. I'm very proud of sharing this space with my dear friend, Hernan here. So without further notice, I will just explain in some minutes, in less than a nutshell, what does nanoscience and nanotechnology mean, at least from a very basic point of view. And then I will give some very fast examples of chemical applications from the field of chemistry. Fortunately, Hernan will talk probably more from the size of the optics and from the physics. And this is very interesting because we have here today some interdisciplinary chat about nanotechnology. well, what's nanomaterials? What's nanotechnology? Basically, is working in the scale of the nanometers. Nanometers is the 10 to the -9 meters. It's a very small distance for us humans, but it's a big distance for atoms. It's a giant step for atoms. 1 nanometer, more or less, is no, it's exactly 1 billionth of a meter, which is our natural scale of movements. But from the atomic point of view, it's 10 hydrogen atoms side to side, and it's probably and it's also 3 water molecules side to side, which more or less is 1/3 of a nanometer. So from an engineer's perspective, or from the perspective of any normal human being, a nanometer is a very small unit, but for a chemist, for a physicist, even for a biologist, is a unit that we use. And for people working in atomic or molecular systems, it's let's say it's our scale of work. However, very nice things happen when materials has sizes, when materials have sizes in the size of nanometers. We are used to materials in the engineering point of view, from bridges, pyramids, or printed electronic circuit boards, in which we know that the properties of matter depend on the composition of matter. We are always taught in the schools and the universities that properties are characteristic of substances, what we call intrinsic properties, or what we call intensive properties, such as density, color, every flux you can imagine, for example, transport properties, conductivity, etc. Melting temperature, and so on. So we're used that we know substances, we know materials, and we ascribe these properties of materials to the composition of materials. And we know that intensive properties do not change with size. We know that we also know very well the molecular and the atomic realm, in which we use the quantum laws typically in order to explain properties, such as the color of dye molecules of colorants, or the behavior of any molecules, of the respiratory chain, or whatever. So we know very well what's happening from the atomic and molecular point of view. We know very well what happens with substances, but up to almost 40 to 50 years, there was a kind of gap in the knowledge and in the real applications of matter, which have sizes in the nanoscale level. What we call nanoscale, substances that have sizes, objects that have sizes in the sizes more or less between 1 and 100 nanometers. Something strange happened that I will tell you. So we call the nanoscale, the scale of length of these materials, and it's typically from 10 to the -9 to 10 to the -7 meters. And this is the scale of nanotechnology. The interesting thing here that this is a double frontier. This is a country with 2 frontiers. We can get to this region of matter from above, from the top-down approaches, making things smaller, or we can go from the atoms and molecules that constitute matter upwards to make these nanomaterials. So nanoscale is in between 2 scales that we knew for some time. But this is really novel. And why is it novel? Because materials, when they are small, they are not only small, but size matters in their properties. In the left panel here, you have this golden coil. This is a wire made of gold that you can use, for example, in electronics for making connections. And you can identify that gold has many very well-known properties. Gold is brilliant. Gold is golden color. Gold has an elevated conductivity, and has also, for example, a fusion melting temperature of 1063 degrees centigrade. And whenever we cut this gold into pieces, or we grind this gold into smaller pieces, or in golden powder, we have always this golden color, this same conductivity, and the same melting temperature. But what happens when gold is smaller? These flasks here, these are flasks that contain solutions of golden particles. But these particles are not golden anymore. It's observed that, for example, if you have a gold particle which is small and about 50 nanometers diameter, it presents a red color. Whenever you increase the size a little bit, you get deep ruby colors, and then when you go to 60 nanometers, what happens? You have a purple color. And then we go to 100 nanometers, you don't have suspended particles anymore, but you can have a kind of precipitate and kind of light scattering. So here you see that all these particles are gold, metallic gold, but the metallic gold is no longer golden, but is red, purple, ruby, depending on the size. This is marvelous. It's telling you that when matter is contained in materials that are in the size of the nanometers, the intrinsic properties are totally different. And it's not only about the color or about the conductivity. It's also about the melting point. This is a very old experiment in which the melting point of gold also is recorded as a function of the size of the particle. This is a very clever experiment made in 1976 by Buffat and Borel. And there is a very clear relationship. This was made under a transmission electron microscope, and they saw this what you see here is a transmission electron microscopy of one gold nanoparticle. You can see here some white spots. This is the space between the atoms. These dark dots here correspond to the gold atoms. What you see is a crystalline structure of a particle, and you can measure, you can change the temperature and see when these atoms become disordered, and then you have the melting phenomenon. So you can record the melting temperature as a function of the size of this particle, and you obtain this logarithmic scale, this logarithmic dependence. What is this telling you? This is telling you that gold melting point is indeed dependent on the size of the particles. Why is this so? Because you have many atoms, a great fraction of atoms on the surface, and this presence of atoms on the surface destabilizes the particle, and the smaller the particle, the less stable it is. The easiest is this particle to melt. So basically, we were cheated at school. As this meme says, all teachers told us that properties of matter do not change with the size of the system. But when the systems are nano-sized, welcome to nano. Properties changes with size. This is the most evident thing that happens. So there are several characteristics of nanomaterials and nanotechnology. The properties now depend not only on the composition, but also on size and shape of the material. There's an enormous surface to volume ratio. A lot of atoms are proportionally the surface, the smaller the material is. And then you can change, you can use a lot of techniques from the chemistry, from the physics, from the material science realms. You can use a lot of different strategies in order to modify, for example, materials, surfaces, to combine whatever you want in very complex nature. And further on, you also have nano-objects, and the sizes and the interactions between the nano-objects are compatible with the sizes and interactions, for example, of biological objects such as enzymes, cell membranes, etc. So these features, these characteristics are very flexible, and they open the world to a lot of novel properties, because now properties do not depend only on which material do we have, which substance do we have, but which is the size, the shape, and also the interactions and the visibility. So we have some coupling. Okay, good, thank you. So nano, of course, is a very broad field. I won't talk about a very broad field. I will have to be very brief. But basically, nano is also interdisciplinary. So in any nano project, you have people from the engineering camp, from the biology, from the material science community, and with a heavy basics in chemistry and physics. There is also a lot of developments, and in the last 20 to 30 years, they have been major, and several Nobel Prizes have been awarded to strategies for nano, from the atomic force microscopy to the last year prize of chemistry to molecular machines, to nano batteries, etc., to effects in the giant magnetoresistance. All these Nobel Prizes in the last 20 years have been awarded to people developing the nano world. But there are also a lot of products. This database, this is very updated, lists more or less 9,000 products based in nanotechnology of about 2,500 companies. And the global market for nanomaterials is in the hundreds of millions of dollars. So hundreds of billions of dollars, sorry. It's 1/4 of the Argentine GDP. Where is nano everywhere? We have nano in cars, in the tires, in the batteries, in the LEDs, in the windshields, in the textiles for the seats, in the brake liquids, in many systems of a car. There is today nanotechnology. There is nanotechnology in the hard disk industry. And one of the Nobel Prizes I mentioned with the giant magnetoresistant effect was the development of high-speed readers for data. Other nanotechnologies are stored in the disk, in which have very small magnetic dots that store the information. There is nanotechnology in architecture. For example, this church in Rome that's always white and clean, because it's built with a self-cleaning material. And we in Argentina have, for once, won the Davis Cup thanks to Juan Martín del Potro here, and his tennis racket that also contains nanotechnology. To give you a very fast idea of how what's the time between the development of an idea and the market, this is a very interesting case. These flasks, these luminescent flasks you see here, are a material called quantum dots. These quantum dots are small nanoparticles. These are transparent nanoparticles because they're very small, they don't scatter light. And they, once illuminated with UV or blue light, they can emit, they can re-emit, they can luminesce in several different colors. And this emission is different, not because the material is different, but because of the size of the particles is different. Larger particles emit light in the red. There are fluorescent particles that emit in the red. Smaller particles emit in the purple or blue. So this is very nice. This is the fluorescence of semiconductors was very well known in the optics of semiconductors from the 50s and 60s, and some Russian theoreticians like Ekimov began working in speculating of what happened if a well-known property such as emission of light from a semiconductor, I won't be technical, just state it, what happened if we shrunk the semiconductor to a small scale. And he concluded that they could get different luminescence colors. This was in the 80s, more or less. 15 years after, the group of Mungi Bawendi in Boston began to synthesize these materials that were perfectly monodispersed, perfectly small, and perfectly tunable, and with Paul Alivisatos and Chris Murray, two excellent synthetic chemists, developed all these strategies to bring up these particles and make this theory reality. In 2001, Alivisatos put this small company, small startup called NanoSys. Alivisatos is one of the greatest chemists, materials chemists nowadays. And in 2015, Amazon saw that these materials could be useful for screens. These materials were a curiosity, then were used for cell tagging, but then Amazon so that this was potentially commercially useful, and included these small dots as inks for making screens for the Kindle Fire. And there it began a race for new screens and new optical devices, and then we arrived, for example, to the QLED technology for TV screens. This business is moving from $600 million to $3 billion in 4 to 5 years. So it's a very, very interesting business with very, very high scientific quality injected inside. This is just an example on several, about 40 years after the first idea, you have very nice inputs. Okay, there are other applications of nanoparticles. Here you have a glass from the Romans. This is called the Liquidus Cup. It's in the British Museum. You can, when you illuminate the cup from inside, you have this red glow. When you illuminate from outside, you have this green color. This is because gold nanoparticles can absorb light and do not reflect light. So you see this different illumination. This you see a similar effect here. The colors you see depend on the type of particles you use and also on the size of the particles you use. These effects in playing with the optics of nanoparticles are also advantageously used in, for example, creating detectors, sensors. Practically all the tests for pregnancy kits, you know, when you see these purple lines, are due to the presence of nanoparticles that are conjugated with antibodies that detect different biomolecules in a very selective way. And these optical signals of the nanoparticles can be also taken advantage of. This has been taken advantage by many companies, in particular in the University of San Martin. We have ChemTest, where here we have Diego Comerci and Andres Cioccino, and we don't have Juan Ugalde because he was taking the picture here. Three biotechnologists, fantastic researchers and entrepreneurs that put their own company and created a lot of different tests, for example, for veterinary and for applications now in COVID-19 as well. Some other daily applications of nanotechnology, if you see these pictures of cities, like this old picture of New York in the 60s, the smog here on the modern cities was mostly due to incomplete combustion of or bad combustion of cars, mainly, in a great part. So you have a lot of light scattering and toxicity of these particulate systems made by finely divided carbon combined with nitrogen oxides and carbon monoxide, which is a very toxic mixture, very bad for respiratory issues. And in the 70s, there were some new regulations aiming at improving the exhaust and the combustion in motors. And one key player here is the catalyst that every car has, and each catalyst you have in your cars is basically a nanotechnology factory. It's a very, very fantastic engineered. It's a fantastic engineered reactor that depends on very well-crafted nanoparticles, and these nanoparticles are made of precious metals, and these nanoparticles catalyze the decomposition of carbon and the decomposition of nitrous oxides. So this, in 30 to 40 years, this nanotechnology made a lot of work for health and environment at the same time and reduced smog to acceptable levels. Now, in the next few minutes, I will show some nanochem applications. Here are some chemists at work that you might know from TV. Chemistry is one of the bases of nanotechnology. We can make any kind of particles, as Richard Feynman stated in a very, very famous and groundbreaking conference. There's plenty of room at the bottom. We can do a lot of things with nanotechnology, but one of the bases of nanotechnology is making nanomaterials in a very tailored way and in a industrially scalable way. So in these, chemical methods are very nice. Here you have some iron oxide particles. Here you have some metallic nanorods, 200 nanometers by 50. Here, these particles are very, very beautiful, but it's not only the beauty. Remember that properties are linked to the composition of the particles and also to the size. So chemical methods have to deal with very stringent conditions in order to have totally controlled size and totally controlled structure, in order to keep their properties tuned with the size. So there are a lot of systems now, and there are a lot of different providers of nanoparticles of high quality, and this is more, and these nanomaterials are cheaper day by day. There are some applications for example, for environment. One very interesting one is the ability of having materials with a high surface area. Whether you have small particles with a lot of available surface, you can absorb pollutant. Or you can have porous materials, for example, like these materials we make in the lab, that are also a trap for pollutant. So there is a lot of filtering systems for example, taking care of arsenic or other pesticides or contaminants. One example we made in the lab, we made it on the Atomic Energy Commission. It was the thesis of Veronica Lombardo. We developed materials that selectively could trap copper. This is a problem of the mines. In copper mining, there is a destruction of the copper mineral, there is a dissolution, and the water gets contaminated with some copper. Here, we designed a material that was able to recover copper and be recycled. The mining industry was not interested because the laws of the country had some maximum contents of copper that was within what the law said, but they were, however, toxic. But we went to the mining industry and told them that they were polluting and that this might be a useful material to avoid pollution. And they say, we're not polluting. I say, well, but then you can also recover the 10% of copper that you are losing there. Now it's interesting. So all these materials are very nice, but to sell them to companies or to use them in real applications, they have to have a life cycle analysis, which is very, very important. Materials that act in an environment, for example, materials that are useful for removal of harmful ions, such as heavy metals, should be able to be recycled, should be able to be properly disposed, should be able to be reused in order also to keep with the atom economy. Another interesting work, this was published this week. We worked with a company, with Texan, a company that is from a group that treats all the waste of the Buenos Aires and Cordoba area, and it was a collaboration between our university and the Atomic Energy Commission as well. We basically took e-waste. E-waste is, you take your old computers, old cell phones, old fridges, everything, and this is globally a waste of metal and also of printed board circuits. And the concentration of gold here is about 300 grams per ton of material, which is higher than in the mines in the mountains. So we took 4 years to develop a sound protocol to recovering to recover precious metals here from e-waste directly to a high added value material such as gold nanoparticles. We made a direct switch from the usual methods recover gold or platinum or silver from melting and very recovery systems that use a lot of energy. We use a very mild energy system, and we recover directly, for example, in this case, the gold, as a material that is useful, for example, for sensing and detection, which is nanoactive, let's say. This was also patented and just published. This is just to show you that one of the objectives of nanotechnology is to collaborate in the atomic, in the economy of atoms, in the circular economy, how to recover atoms, how to recover them into systems that are able to be totally controlled. And this is interesting because you can recycle strategic metals. The same thing you can do with magnets, for example, which have rare earth atoms that are also strategic. Another very interesting thing, I won't go into details, but it's the use of some semiconductor materials to use light as an auxiliary method to activate a material to destroy contaminants. This is not a Vatican flag. This is the band structure. This is it's a little technical. If you're not technical, don't worry. Basically, a material, a semiconductor material, has electrons here, has no electrons here. These are states where electrons live, where electrons can go. When light is irradiated here, electrons jump. These electrons can reduce oxygen. A hole is here, meaning that this place needs an electron. So this is an oxidant species, this is a reductive species. And then, when you irradiate, you can transfer easily the electron to the oxygen and the hole to an organic molecule that is sitting here. This results in that you can destroy this organic molecule that was sitting here. You can basically burn it to carbon dioxide, and this electron can go to the oxygen and generate, for example, radicals, and these radicals might destroy other molecules. What's the use of this? The use of this is that by irradiating one semiconductor, you can basically catalyze this reaction, the oxidation of a pollutant to form carbon dioxide and water. So this is useful because you use light to decontaminate without the addition of further chemicals. You create the chemicals there. You create the electrons, you create the radicals. So this is very useful in some commercial applications. This process is called photocatalysis. You catalyze the oxidation of a molecule by using light. And this is, for example, applied in windows that clean alone. Self-cleaning windows, self-cleaning cement, for example, here in this church. So this is structural materials that self-clean. This is very interesting and it's totally commercial. There are, of course, more complex things. I won't go into details, but basically we can do also the same. We can receive light, generate any molecules. That in nature is called photosynthesis. They create sugars from carbon dioxide and water. So basically now one very interesting work is to do artificial photosynthesis. The same concept can be applied to create energy. If we can irradiate and we can separate one electron and one hole, then they can recombine across a circuit, and this is a solar cell. And solar cells, of course, are well known, but these solar cells using nanomaterials, the first were created by Michael Gretzel, and these solar cells are not so efficient, but they are transparent. So you can have solar cells embedded and integrated into the glasses of an auditorium, such as this in the Federal Polytechnical School of Lausanne. Or now you can have solar cells in Scotch tapes that you can just put everywhere and have small places that can act as solar panels everywhere. Regarding health, we'll go very fast. There are a lot of delivery systems based in nanoscience and nanotechnology. They are not so efficient. They do not cure better, but especially in the field of cancer, all the nanomedicine or the nanostructured medicine is focused mainly on having containers that work very well and that are very efficient in shielding a drug and leading to lower doses. So taking a nanostructured carrier helps the drug to be protected and circulate in the body. And with these nano carriers that are already commercial, there are several therapies, there is not a better, let's say, there is not a great improvement in the efficiency of the therapy, but there is a great improvement in having less side effects. So the life cycle of the person is much better. What is impressive is the test or diagnostic commercial devices. And in nano health, now there are two very nice, interesting trends. One is all the prosthetics, and another one is the implanted sensors for in vivo tracking of different vital parameters, embedded in clothes, in food, everything. One interesting thing here is that really the silver bullet that every nanotechnologist has in mind is to have a system, as kind of nano robot, able to go to a targeted organ and deliver the medicine in a very precise way. This is a very complex task. Things can be working very well, but the body is a very complex task. You have enzymes, you have an immunitary system, you have several limitations there that are, science is progressing a lot, but they are still struggling. And of course, you also have a lot of clinical trials and a lot of regulations that take some time to pass. Imaging is another very, very interesting point. There is an evolution of the delivery species. I won't go into the details here, then you can ask whatever you need. This is a very nice picture of a work we did in collaboration with Marina Simean's group. This Angie Ramirez and Tommy Laporte are working this. These are particles, nanoparticles that have been modified with molecules that guide these particles to go specifically to these hairs. This is a cell surface. These are hairs in the surface of a cell. It's called pili. And these pili have some receptors, and these particles sit on the receptors specifically. This is very nice. But this works very well in vitro. In vivo is a little more difficult, but because when you use these systems in vivo, the enzymes tend to eat these targeting molecules. So finally, there is the dose of injection is not, the fraction of nanoparticles that arrive to a given tumor, for example, is rather unspecific, and it's due to reaction of the particles in the body. This is one of the limitations of the therapies nowadays. This is a paper of yesterday, more or less. That says that. Last but not least, let me show you some nano machines we are also developing in the lab. This is one machine. It looks like boring. This is a 3-layer machine. Which is the machine here? This is a gold nanoparticle. When you irradiate this gold nanoparticle with green light, you heat here. This. When you heat this, heat flows at the outside of the particle. And in the outer side of the particle, you have a polymer. And this polymer, when heated, shrinks. But it's like a sponge. When the polymer shrinks, all the contents of the polymer go outside, like a sponge. So what happens? Here you have a remote control system in which when you irradiate, the system shrinks and lets other molecules out. We are testing these systems as a remote control delivery system. We are published recently, and we saw very clearly that these particles, when you irradiate with light, they shrink and they get smaller. Other things we do at the lab, we have also used porous systems for killing bacteria. We made a company out of this. We're very happy. And this also shows that, for example, beginning with some concept to some real application, to some scaling up, it took us 4 to 5 years, for example. But now we are on track. And now we are in the most stringent part, which is testing this in society. Okay, I won't take any more time. There is a lot of discussion now about if nanoscience and nanotechnology really deliver. Some of the limitations are exactly the ability we have to scale up these materials. And I hope that I could convince you that nanotechnology is really a powerful enabler. We have seen some examples in environment, health, and energy, and the possibilities are very high. We can really control totally and very precisely matter, size, position, functionality. We can even make intelligent materials. We have now methods to scaling up, and we also are complying with circular economy to tailor the properties. Which are the limitations today? Maybe the cost, the regulations, the toxicology. All nanomaterials have new properties, but toxicology is also new and depending on the size. And some societal issues, particularly in the side of energy. For example, will we have very big places to produce energy and distribute, or can we produce energy at home? So this is a societal issue that has to be solved. We have the nanotechnology. We need now to go to the rest of the society. So thank you very much for your attention. I look forward for questions, and I leave the stage to Arnam. Thank you. Thanks a lot. And now I pass to the other, Susana. You are muted.
Hernan, are you there? Yeah. Okay,
yes,
good.
Yes, of course.
Okay, yeah. So your time, Hernan, to your presentation. So we'll switch off our videos. So all the lights, all the bandwidth is with you. Okay. You want to introduce Hernan? Galo, do you want to briefly introduce Hernan?
Ramirez is a genius. That's all. Go on. No, friend and a great researcher, an expert in optics and photonics. He's a scientist in the Institute of Material Science in Sevilla. It's more difficult to become a scientist in that institute than to become Pope. So really, he's a very bright person and a very fantastic colleague.
Well, that was generous. Thank you very much. So I hope you can see my presentation. Just let me know, please. Yes?
Yes.
Okay, good. Okay, so thank you, Galo, and thank you, Susana, for letting me participate in this very interesting debate. It is also for me a great pleasure to share one more time a seminar or a workshop with my good friend and colleague, Galo. And thank you all, of course, for coming and attending this seminar. What I will try to give you today is some examples of how we can apply nanostructured optical materials, which is my field of research, to some problems that are related. Let me just please, here. So basically, of course, there are many big questions, and I don't mean at all these are all of them, but I would like to show you some examples about how nanostructured optical materials can be used to in the field of health, which will basically address the first question, and in the field of energy and lighting, which can be called in general energy conversion, right? I think it is clear that if we want to have a world in which we have a sustainable economy or we have a cleaner environment, we have to develop ways of producing renewable energy that can be, that are amenable for mass production. And nanotechnology, I think, has a lot to say in that regard. I have to warn the audience that there's another side of energy I'm not going to touch, which is energy storage. I'm not an expert in that, and I saw there were some questions that were sent, but I don't think I'm the person to answer them. But my work has been mainly focused on the improvement of ways to generate energy, how to generate it more efficiently. So let me please start by showing you what I mean when I say nanostructured optical materials. I have to warn you also that my talk will be a little bit more technical than the excellent overview that Galo just gave us. So what you're looking at here is a collection of images taken with the scanning electron microscope. You're looking at different structures. So there are corrugated surfaces, three-dimensional arrangements, multi-layers, disordered optical materials. So there's a lot of diversity, and there's also a lot of diversity in the composition that you're looking at. We have metal oxides, polymers, semiconductors, metallic particles. So in spite of all this diversity, all the materials that you're looking at have something in common. And what they have in common is that the optical properties that they present are determined by the way in which we have structured them. So that means that how they will respond optically will not depend only on their composition and therefore on their electronic structure, but on these arrangements that you are looking at here that take place on the order of the tens or hundreds of nanometers, which is what you're looking at, right? But they also share another feature, and is that all of them are porous materials. And I think Galo also is an expert in porosity. And I think this is something that maybe applies a lot to the materials that Galo or myself do, but I think it's a general feature for many people working in nanotechnology. And that porosity, that available empty space, many times is what helps us to introduce functionality in these systems and then apply them to different fields. And I will show you examples of that. So let me just show you briefly when I say that the optical properties depend of the structure. Let me just give you a couple of examples that I think are very illustrative. So what you're looking at here are two different materials based on the same building blocks. This little picture here is a transmission electron microscopy image of latex or polystyrene spheres. In this case, we have arranged them in a perfect face-centered cubic lattice. So basically, this is like a crystal, but instead of having atoms in the crystalline positions, we have large spheres that are a few hundreds of nanometers in size. And with the same spheres, we can make a completely disordered material. So same composition, completely different structure, and therefore completely different optical properties. If we shine light on them and put a screen at the back of the sample or in front, if we make a hole, we can see clearly how the order is reflected in the optical properties. You see this diffraction very clearly, right? On the other hand, if you do the same with this disordered material, you get something completely different, which is this speckle pattern, right? Characteristic of an optically disordered material. So structure means everything in terms of how they interact with light. And I have to say that this is something, even this example very similar to this, you can find it in nature, right? What you're looking at here are two beetles. One of them is shining in blue, as you can see, and the other one is white. But in both cases, they have elytrons that are made of chitin. But in this case, chitin has formed these nice multi-layers, while in this other case, it has arranged, or better, it is not arranged, it's completely disordered. And this is why one is white and the other one is blue, right? So continuing with this and getting closer to the materials that we prepare, you have here another example of how you can control properties with nanostructure. You're looking at three films that have completely different color, obviously, as you can see. But again, here, the composition they have, the chemical composition is the same. They are made of silicon oxide nanoparticles and titanium oxide nanoparticles stuck in a structure very similar to this one that you can see here in this model. Right? What is the difference between them? The only difference between them is the thickness of each one of these layers that is forming this multi-layer structure. And the reason why we can control color here is because the physical principle behind this, this effect, this color effect, is optical interference, which is explained here, and I think the audience is very broad, so I'm not going to go into the details, but just keep this message. Every time you see color around you in fruits, clothes, so everything that has a pigment or a dye, what you're looking at is the result of a process of optical absorption. So that pigment is absorbing part of the electromagnetic spectrum, part of the visible light that reaches this pigment, and the rest is reflected or transmitted. And this is the origin of color in most cases. But here we are talking about materials that don't have any type of absorption in the visible, and yet you can control very precisely the color just by playing around with this physical concept of optical interference, which is central for every nanostructure optical material. Okay, so I said before that one of the most important features that allow us to provide functionality to these materials is the porosity. And I will show you an example of what I mean by that. So let's say we have this porous mirror that we have built on a flat substrate, and this is a rigid system, but we are interested in having something that is flexible. This is what we actually thought a few years ago. And the idea that we had was, okay, let's just try to infiltrate this with a material with very good mechanical properties, such like a polymer. So there are different ways of doing that. And our idea was to get something like that. Let's see if we can make self-standing flexible mirrors that will add a lot of versatility to the use we can have with them, right? So this is what we did, and this is just a summary of a very long project that was very important in my group a few years ago. This was the first highly reflecting flexible mirror that we could make right when we were actually detaching it from the rigid substrate. And you can see that it has flexibility, but it keeps the strong and robust optical properties of the inorganic part, which is the multi-layer, right? The porous multi-layer. So we tested this with a wide range of polymers and different types of porous nanostructure materials, like the one you see in this picture here or here. But now I would like you to focus on this one here. This is the only one that doesn't have any color here. It's just transparent. But this material actually has a strong reflection, but in the ultraviolet regime. We designed it so it would be actually transparent, fully transparent. We used a biocompatible polymer, a silicone, because our idea was to see if we could actually use them as patches to protect newly regenerated skin. The idea was to develop a product oriented to the biomedical industry. And the goal was to see if we could protect the skin, because this is a physical barrier against any external agent, allow us to see through, and at the same time block completely the UV light without absorbing. And there were many reasons to prevent absorption in a polymer, because basically absorption is going to deteriorate the materials. So this is what we did. This little spectrum here, this little peak, is the DNA genotoxic spectrum of sunlight. So basically, we took this from the journals of dermatologists and designed a mirror that matches this genotoxic spectrum. So basically, we did the tests. I'm not an expert in this, but we collaborated with a biomedical group in Bionand in Malaga, and they used artificial skin and covered this skin with our film and other test materials. The idea here is that if after exposing your skin cells to UV light, you see green, is that you have killed them, and if not, you have succeeded. And these are the tests for our film. And this is actually a similar result that you can get with a highly absorbing highly ultraviolet absorbing material. So it was very effective, right? But no absorption, everything is reflected. Okay, so this is my first example of an application, if you want, of nanotechnology in health using nanostructured optical materials. But here, what I just showed you, we are putting into practice what we call the far field properties of these materials. So basically how light is reflected or transmitted. But there are many other interesting things that happen in these materials. But if you get closer, let's see, we could see inside. So this is a simulation, what you're looking at here, of how the optical field intensity, how light intensity is distributed inside one of these materials. So just by playing around with the thicknesses of one of these multi-layers, as you can see here, you can obtain the following results at certain positions that are well defined, right? So these are the layers. This is the depth. This would be the depth in the structure, and certain wavelengths. You can get very intense light field enhancements, right? And a similar thing happens when you use metallic nanoparticles. I chose these gold nanostars as an example, and this is also a simulation, and you can clearly see how when you illuminate them, light is going to, light intensity is going to be enhanced around the nanoparticle. So you have to believe me, because I'm not going to get into the math of it, that if I place here or here a material that can absorb a little light, I can make it absorb a lot. Or if I place a material that can emit a little light, I can make it emit much more, right? So this property can be used to enhance the optical properties of other materials that I can place here, right? And I'll show you an example. This is experimental, it's not anymore a simulation. So we established a collaboration with the group of Bettina Loch at the Max Planck Institute, the Solid State Research Institute. And what we did was to combine nanospheres made of polymer, one containing a dye, so they can emit light, with two-dimensional antimony phosphate that Bettina was preparing, and with our silicon oxide and titanium oxide particles, and created a structure like this one that you see here. So this structure presents an optical resonance, a field enhanced at this position, just like the one I showed you before. So what happens with this type of resonances, right? Let me just go back for a second to the previous one. So if I have a resonance like that, it's going to be extremely sensitive to any change in the geometry or any change in the dielectric environment. So if there's a change in the composition around them, even if it's very small, it will reflect clearly in the optical properties, right? So what happens here? We have a well-defined optical resonance, and we can get a strong emission from these dye spheres here, right? So we get a very strong emission of light. But if I expose this to humidity, the nanosheets are going to start increasing in size. They swell. And as they swell and I change the geometry of the whole structure, this intense emission that I was talking about will no longer happen. And this is the experimental result. Basically, when you expose to increasing humidity a system like that, you start with a very intense emission in the green that disappears above a certain level of humidity. Or you can make the opposite design and start with a material that doesn't show any luminescence for low humidity, and above a certain humidity starts emitting. So this is just a proof of concept of how you can combine many different nanomaterials, and this is typical of nanotechnology as well, combining many different types of materials in complex structures, to obtain a sensor, a photonic sensor for humidity, for changing humidity. And this takes me to another example that is not from my group, but I asked a colleague of mine in the Spanish Research Council to send me a slide, because I thought it was relevant, especially in the moment that we are living. So since the COVID-19 pandemic erupted in Europe, the European Commission is funding, very well funded, actually, a few projects targeting different aspects of this pandemic. And there's one project of this that is actually being led by a Spanish group, which is the group of Professor Laura Lechuga at the Catalan Institute of Nanoscience and Nanotechnology. And precisely what she is trying to develop is an optical sensor, a photonic sensor based on structure or nanostructured optical materials. And I'll show you briefly how it works, but I have to just stop my laser pointer so I can stop the video. Okay, so let me just show you briefly how is the design. So what you have here, it's a metallic film, right? Which is trapped between two dielectric films, right? So here, because I have this metallic film, I will have a strong field enhancement very close to this metallic film. It's not plot here, but you have to believe me in that. And basically what happens is that if light travels very close to the metallic film, then I will have a very strong interaction of light with this system, right? So let me show you a little bit more. So now you will see a cross section of these, right? And this is, oh, I'm sorry, excuse me. I will start again. Yep. Yeah, so here you see light is traveling. There's no resonance plot here, but this light is interacting strongly with this system. And as you can see here, there's these blue molecules are antibodies that are receptors for COVID, for the coronavirus, right? So if now we let a fluid to go through and the coronavirus reaches this region, what will happen is they will link to these antibodies and the dielectric environment will change. So that will cause a change in the optical signal that we can detect here, right? So this is just obviously a promotional slide that I was allowed to share with you. And it's a project that started in April, if I'm not wrong. So they really put together very quickly a team to achieve this in the middle of the confinement here in Spain. And this is what I wanted to show you about how you can apply some examples. Obviously, there's a lot more about the application of nanostructured optical materials in health. I will move on now to energy, and what I will start by talking a little bit about nanostructured solar cells. Actually, Galo already was showing you some examples of a dye-sensitized solar cell in his talk. He also mentioned quantum dots. The chart that you are looking at, let me just please give me a second. Yeah, so this chart that you're looking at, I got it yesterday from the webpage of the National Renewable Energy Laboratory in Colorado, which is one of the few centers in the world that certifies the efficiency of solar cells. So I selected as only those corresponding to emerging photovoltaics. All these are photovoltaic technologies that some of them are highly promising and that are being studied these days. The interesting thing, or the interesting relation with the talk today, is that many of them are nanostructured solar cells, dye-sensitized, perovskite cells, the tandems. Basically, I would say that all of them are nanostructured solar cells because they have some component that has a nanometer or 10 of nanometer size. I'm going to focus just on one of them today, which is the perovskite solar cell, although I worked a lot in dye-sensitized solar cells, but I just wanted to bring a few examples, right? So I would like just to justify why people are so excited about perovskite solar cells. Maybe if you are not familiar with the field, you haven't heard about them, but it's something that it's been a little bit everywhere, as it happened with graphene, right? The thing is that the reason why they are attracting so much attention is in this chart. If you look at the evolution of the efficiency of all these cells, you will see that the one that is growing the fastest is actually perovskite solar cell. This is also a variation because this is a combination of a perovskite with a silicon solar cell in a multi-junction device, right? So the single junction is already above 25%, and this is 29% in just a few years. It's true that these are research cell efficiencies. It's not modules, which is always a little bit less, but it's very promising. However, the material on which they are based, and I'll show you now, give me just a second. I'm sorry, but my presentation stopped.
No problem.
Give me just a minute. I hope it will go back. Okay, are you still looking at the shared screen?
Yes, yeah.
Okay, yeah, it's just that it's, I think I'll have to, yeah. Okay, here, it's back. I don't know if are you still seeing it?
Yeah, that's
Okay,
fine.
perfect.
Yeah.
I'm sorry, for some reason it was hanging there. Okay, so this is the structure of a perovskite solar cell. And as you can see, it is by definition nanostructured, not only because we use a nanostructured scaffold, which is this mesoporous titanium oxide that is fully infiltrated with the perovskite, but also because every layer in this system has from a few nanometers to a few tens of nanometers, sometimes 100 nanometers thickness, right? So there are a couple of things that are very relevant regarding this device. One is that it is a very efficient absorber, the perovskite, so it's difficult to improve its absorption, but there is a drawback in this material, and the drawback is that in the composition of the standard perovskites that are used in this field, there is lead, and lead always poses an environmental problem for it's going to be difficult to you know, there are a lot of regulations everywhere against the use of lead, as they are against the use of cadmium in devices, right? So one of the reasons why we would like to improve the efficiency of absorption is to be able to have very thin films absorbing very efficiently. However, that was not our first approach. I'll come back to that later. The first thing we tried to do was to substitute this porous scaffold by one of our porous mirrors. The idea was to try to tune the color of this cell to make it more attractive for building integration and in general for integration as a whole, because color is always a value in terms of the potential commercialization, right? So this is what we did. We did it in collaboration with the University of Oxford, with which the one that is considered the inventor of this, which is Henry Snaith. And with his group, we developed this nanostructured photonic electrodes, in which instead of having just titanium oxide, we have titanium oxide and silicon oxide arranged in a multi-layer, and this multi-layer is capable of changing the color of the cell. There's a certain sacrifice in the efficiency that you get, but it still is higher than in most other emerging photovoltaics, and you can control the color very efficiently. As I said before, the other reason why you would like to play with the optical design of this cell is because you would like to have a maximum absorption of light in the minimum thickness possible. And I have to say that this is a common problem in the world of photovoltaics. The reason basically is that if I want to absorb light very efficiently, because basically what a solar cell does is it absorbs light, charges are generated, and you have to take them out to get an electric current, right? So once charges are generated, they have to travel to the metallic contacts. If I want to absorb a lot of light, the only thing I have to do is to make my absorbing material very, very large, and I will absorb all light that I want. But if I do that, I'm forcing charges to travel very long distances. And when they travel very long distances, they can recombine and you can lose them. So there's always this compromise, right? You need to absorb light efficiently, but at the same time, collect the charges efficiently. And this is why the optical design of a cell is so important, because you always want to have maximum absorption in the minimum thickness possible, right? So we had been playing around with this concept for a few years in other solar cells. So we applied the same concept to perovskite solar cells. We tried many things, which I'm not going to tell here today, but I will show you the example that I think is more promising. What you're looking at here is a simulation, because every time we start a project, we start simulating. What we did was to see what the effect on the absorption of the perovskite, of a thin film of perovskite, 200, no more than 300 nanometer thickness, what would be the effect of having a metallic particle inside the film. We wanted to take advantage of this near field enhancement I was talking before to improve the efficiency, right? So we tested every possible metallic particle that we could find and discovered that most of them would have a positive effect, but especially silver nanocubes. So this is what we did experimentally. This is the experimental realization, not of the cell, but the integration in the perovskite film. So this is a 200 nanometer perovskite film with metallic particles integrated in it. These are the metallic cubes that we synthesize for that. And this is the demonstration that you can actually improve the absorption in a wide spectral range, just like the theory says. So this is theoretical, this is experimental. Okay, and I'm also taking a little bit longer than I thought, but I would like to finish showing an example of application in a different field, also related to energy conversion. But in this case, we convert electricity into light, right? Which is the field of light emitting devices. So basically, first of all, let me just tell you briefly what is the structure of a LED bulb that we all have in our home today, right? Basically, there are two main elements in a LED bulb. You have first an electroluminescent light emitting diode that is going to shine blue light, right? And that blue light is going to impinge, is going to reach this coating, this yellow coating, which is made basically of large crystals of a material called cerium yak embedded in a polymer. Basically, those crystals are going to absorb part of this blue light generated in the diode and transform it by a process of photoluminescence in this broadband of green and reds, and yellows and reds, right? So, and this is the origin of the white light in an LED, right? There's some blue light that goes through because it doesn't get absorbed by the coating, and then there's the greens, yellows, and reds that are generated by this photoluminescence process, right? So one thing that you have noticed probably immediately is that these coatings are opaque. They don't let, they are not transparent. Okay, you cannot see through. And there could be many things that you can do in terms of playing around with the spectrum and the directionality of light if you can do photonics and do optical design with these coatings. However, the first step to do that is to be able to fabricate transparent coatings of these phosphors. So this is what I'm going to show you, and these are my last slides. So there's one project now that is being conducted by one of my youngest coworkers, Gabriel Lozano, that is focused on developing phosphor-based photonics. And the first step, I'm just showing that, is that, or the idea and why it is so related to the talk today, it's because the way to make a phosphor coating transparent is to start with nanomaterials. So you start with these nanoparticles, right? These are nanophosphors. So basically rare earth doped crystallites of different compositions. And you can make a thin film and you can start heating it, right? So you heat it because you need that to get a very good emission. And you see that even at very high temperatures, you still get a very good transparency. And this is because you start with very small pieces, you start bonding and sintering them together, just like you see here, right? So the result of this is that you can get completely transparent coatings, as you can see here, but when you excite them, you get this white light emitting, right? So this would allow you, for instance, to get a display that is transparent, and when you excite it, you get the white emission that you want. Okay, so this is everything I wanted to tell you. I just would like briefly to thank my group for all the work and our public funders and our private funders. And obviously, I would like to thank you for your attention. Thank you very much.
Thank you very much, Hernan, and thank you very much for a wonderful talk. And then Galo, if you can come up to the screen, we are going to answer some of the questions. There are so many questions that now I've lost track. You answered many of them, but then let me see. We have Juana asked a question. I was wondering if you recommend a book about nanoscience for those who are getting into the topic. Is there a book?
There are many. Susana, but you have to let me initiate my video because I'm blocked.
Ah, okay. That's Carlos there. And and how do I do that?
I don't know. You are the master.
We are in trouble, Galo.
Okay.
Okay. Julio, can you
problem.
help me? Because if I don't see, I know how I have to do.
Anyway,
you keep talking, and I'm going to try and try to see you. I saw you there. Okay.
Okay. No, I can recommend. I wrote two books about nanotechnology. More. One is a dissemination book, very basic. It's from Paidos. I can give the details by chat if anyone is interested. I'm getting rich with the book. It's like selling 2 books per year, so 3 would be a 50% increase. No, it's very basic. It's called ¿Qué es la nanotecnología? You can have it in any library, bookstore in Buenos Aires. And I have another book by Eudeva, which is a little more technical. It's called Nanotechnología. It's 10 years old, but it's still you can read. It's a little more technical. So this is from books I wrote. And then there are several books. The books of Jeff Ozin about nanochemistry is very nice. The book of Ratner is very old, but conceptually is very nice. There are several books.
I think the book by Ozin in nanochemistry is a very good introduction, and it's not
beautiful.
complicated.
No. It's very nice.
It's easy to follow and pretty complete.
Yeah.
Okay. So let's go to the next. We have so many questions. I'm going to try. There's one question from Maria Rosso, and she says she's working with phreatic water remediation. If you are aware of any development to apply nanotechnology to this process?
Not me, to be honest.
Well, there are several, as nanoparticles are small, I'm sending to all some links where to find books. For nanoparticles are small, and they can be easily dispersed in water, for example. And some people work injecting these colloids in phreatic deposits. So the particles get retained in the pores of the rocks, and eventually these particles can absorb pollutants. One example is the Argentine company Nanotech. I don't know if, let me see, the question is here. Oh. Sorry.
The one about
remediation.
Yeah.
Yes, Maria Rosso.
Could you tell me, yeah?
There is one company, Nanotech, in Argentina. They are working in nano-iron particles. It's metallic iron. It's very reactive, but you can keep nano-iron in suspension in a closed container. Then you can inject that directly in la napa phreatica. I don't know how to say in English. And the iron, for example, is very well known for retaining arsenic. So they are using this as a scavenger of arsenic species. And other similar minerals or very well dispersed nanoparticles that are functional can be injected in some way, and there are some treatments on that. Yes, but I suggest you go to Nanotech site. Nanotech is Nanotech with K, and then or contact me and I will give you more advice on that.
Okay, so here there's another question from Roberto Candal. He says, thank you, Galo. Do you have information about nanoporous materials with catalytic thermal activity at room temperature for organic chemical oxidation?
Catalytic with no
The
light?
question comes from a chemist, so...
No, it's a question from an expert, not from a chemist. Roberto is very
Yeah.
a real expert.
It comes from Roberto Cantal, that's why I said not...
I don't... I know that most of the porous materials I know have activity at high temperatures or activated by light, but it depends on the organics. I think that now many people are using all these advanced oxidation techniques in temperature or with auxiliary regions, but not that I know. But I'm not an expert in that in the field of cold catalysis. Now there is a lot of work in the community of catalysis aided by light, like photocatalysis, but by using light, but not at ambient temperature in an easy way. Because for that you need metallic centers that have a very labile coordination. So it's not so easy, it's not so stable as well.
Okay, so I think that in order to keep... Yeah, there's hundreds of questions here. I was going to say to choose one or two more, and when we will continue by email, but then if there's any other question you see in the chat you want to answer.
There were a lot of questions for Hernan in the multi-layer system.
I can answer them if you want.
Yeah, that's
an
interesting question from Roberto Candal again. Yeah, which is the state of the art of the perovskite scale-up?
Well, there are modules already being made. I believe the highest efficiency in a module is around 16–17%. So it's not the 25 of the record cell that I showed you before. Mm-hmm. So it's, but yeah, there are many people doing a scale up in this field. There's actually all over the world. Here in Europe, Italy is doing a lot. And actually the people that used to work in dye-sensitized solar cells, now they moved to the field of perovskites. And the main problem that the field has to face is stability. Mm-hmm. This is the thing, right? So I've seen very good results in conferences of once they can seal them very efficiently. But something that is a little bit of a paradox is that the perovskite is highly there are a lot of photo-induced processes that are triggered by photoexcitation. This is the main problem it has. If you can seal them very well, I think you can prevent that, and probably with some previous treatment. But there was another question before, like a few questions in the chat above. Someone asked, how do you keep the particles together in a layer?
Yes,
so
Mara.
Yeah, Mara. So basically, you can do different things. You can hit them and they will sinter slightly, and which is something really good. Actually, Galo showed like a paradigmatic example, which is how you can actually I think it was melt gold, right? A much lower temperature when you decrease the size. But the same thing happens with metal oxides. If they are very small, they sinter at much lower temperature than what is typically required in the ceramic industry, right? So you go to 400, 500 degrees Celsius, and you can actually compact and make something a little bit more robust. If you're going to infiltrate a polymer, you don't need to do that because the polymer itself is going to keep the whole thing together. So that depends on how you're going to use them. There are different ways to bind them, right? And there was another question, excuse me, which was about the toxicity of titanium oxide nanoparticles. I know that there are titanium oxide nanoparticle compounds that are FDA approved, so to say, but that depends on the specific type of nanoparticle. It's not that they are approved as a whole, right? Mm-hmm. And the same thing happens with silicon oxide, aluminum oxide, and other metal oxide nanoparticles that are used in toothpaste or in. But you just have to keep in mind, at least in the applications I was proposing, they are they never go inside the body, which is the main problem, right? To use it as a patch, you also have to obviously to follow some regulations, but they are not so restrictive as if you're going to inject it in the bloodstream, right? Yeah, I don't know.
This is, sorry, may I make a comment on this? It's a very important question, because as nanoparticles have properties that depend on the size and shape, all toxicity now depends on size and shape. So some types of nanoparticles are FDA approved, and in fact, whenever you drink orange juice like Tang or something like that, you are drinking silicon dioxide or titanium dioxide. I'm sorry, it's not orange, it's a paint. And this is FDA approved, of course. And of course, it depends a lot. Skin toxicity and blood toxicity is different. And there was a big issue some years ago with titanium dioxide and zinc oxide that were used in formulations for sunscreen blockers, sun blockers. There was you use typically for when you go to the beach and put your sun protective agent. Typically, old formulations were made of organic molecules. Then they moved to titanium dioxide, the sunblock, the white stuff. Then they moved to nano materials because they are transparent, so it's easier to sell. And the problem there was, are these materials activated by sun and generating radicals on your skin, and maybe they can trigger cancer? And there have been a lot of trials with different formulations, and basically after several years of having a lot of debate, finally the majority of commercial zinc oxide and titanium dioxide are harmless and can be used in that formulations. But it required a lot of work, a lot of work, even for skin treatment, which is superficial.
Yeah.
Then you have another one that if you try with another material instead of perovskite, like a metal organic frameworks in photovoltaic cell device, Hernan, I think.
No, I never tried to introduce metal organic frameworks in a photovoltaic device. It wouldn't play the same role though, right? Like a perovskite is a light absorber and a very good conductor. A metal organic framework, which I'm not very familiar with, I just read a few papers. I don't think can substitute the perovskite itself. Maybe you can use it as a scaffold and can provide you with some interesting properties. But to be honest, I don't know.
Well, they have different conduction mechanisms. Yes, metal organic frameworks are more like molecular materials, so it's not the same performance regarding charge separation. But there are some essays on that, but it's not common.
I think you've been very generous with your time, Hernan, and I think it's now time for you to have a dinner.
Yeah. No, don't worry.
But yes, so everyone is saying thank you to you. Thanks very much, Hernan, for joining us. And thank you, Galo, for organizing such a wonderful event. And we'll keep in touch. And hopefully in 2 years' time, you're going to come to UNSAM again.
Yeah, perfect.
Mid-August, every 2 years, we have a planned seminar. That's how far ahead we plan. Okay,
it was a real pleasure.
Yeah.
It was a pleasure for me too. Thank you very much.
It's a pleasure to have this audience. Thanks for the audience for coming, and then we'll have another event in 4 weeks' time. Yeah, we still don't know what it's going to be about. Okay, thank you very much for coming, and we are going to switch off the screens now.
Okay, bye-bye. Thank you. Let's keep in contact. Thanks a lot. Chao, Hernan, gracias.
Chao, muchas gracias a todos. Chao, chao.
Cariños a todos por allí.
Bye.
Igualmente, chao.